This object is simply a piece of another solar system that was expelled, and it has been traveling through interstellar space for hundreds of millions of years, billions of years, we don't know.
Hey there, space enthusiasts. Get ready to blast off into the cosmos with us. Welcome to Spaceverse, where the universe is our playground and curiosity knows no bounds. Join us on an interstellar adventure as we dive into the depths of space, uncovering its mysteries and marvels. From the secrets of black holes to the landscapes of alien worlds, we're here to ignite your imagination and expand your cosmic horizons. With mind-blowing visuals, expert insights, and the thrill of exploration, Spaceverse is your ticket to the ultimate cosmic journey. So strap in, hit that subscribe button, and let's embark on an epic voyage together into the vast unknown of Spaceverse. Our beloved solar system boasts an array of celestial bodies ripe for observation, analysis, and exploration. 1 star, 5 dwarf planets, 8 planets, 146 moons, 3,800 comets, and approximately 1.3 million asteroids. Yet, to the curious minds of Earth-bound astronomers and researchers, this extensive collection of rocks, gas giants, and icy fragments was starting to lose its allure. Let's face it, after spending so much time with the same old inhabitants, the desire for encounters with new arrivals, a mysterious visitor offering fresh perspectives on the universe, becomes irresistible. For years, the astronomy community speculated about the existence of objects drifting into our solar system from beyond its borders. This speculation turned into certainty in October 2017 when a peculiar wanderer caught the attention of a Hawaiian telescope. This was Oumuamua, the first confirmed object from another star to visit our solar system. Was it a typical asteroid or comet, perhaps a remnant of a deceased planet, or more tantalizingly, a forgotten artifact of an advanced civilization? Well, maybe, but probably not. On October 19, 2017, the Pan-STARRS 1 telescope at the University of Hawaii, funded by NASA's Near-Earth Object Observations program, was scanning the space around Earth. Observers spotted a new object 33 million kilometers away, dubbed 1I 2017 U1. What caught their attention was its astonishing speed as it zipped through our solar system. Typically, objects originating within our solar system travel at about 69,500 kilometers per hour, but this visitor was speeding along at over 314,000 kilometers per hour. For context, it could have covered the distance from Los Angeles to London in just 100 seconds. Was it a comet? Was it an asteroid? The object showed no signs of cometary activity, such as leaving behind a trail of gas and dust, indicating it was likely an asteroid. But wait a moment, this asteroid seemed to be accelerating slightly, behavior more typical of comets. As we'll explore, the true nature of the object would remain a topic of debate for years. What was clear to the observers in Hawaii, however, was that they had just identified an ISO, an interstellar object, a vagabond that had journeyed from a distant star to our solar system. This was a significant discovery. According to NASA, 1I 2017 U1 was the first confirmed object from another star to visit our solar system, emphasis on confirmed, as astronomers estimate that ISOs pass through our system about once a year. These objects are relatively small and thus exceedingly difficult to detect until Pan-STARRS 1 came into play. 1I 2017 U1 could be considered a messenger carrying valuable information about the composition of distant celestial bodies. This prompted the Hawaii observers to give it a Hawaiian name, Oumuamua, which translates to a messenger from afar arriving first. After its initial sighting, Oumuamua underwent close scrutiny from other observatories, including the Very Large Telescope operated by the European Southern Observatory in Chile. The ESO's Very Large Telescope, yes, that's its real name, tracked the object's orbit and brightness, providing images to a team led by astronomer Karen Meach at the Institute for Astronomy in Hawaii. Their observations revealed that Oumuamua's brightness varied by a factor of approximately 10 every 7 hours, suggesting that the object was spinning or tumbling along its longer axis. Meach concluded that Oumuamua likely had an unusually elongated shape, about 10 times longer than it was wide, with a complex, irregular form. Quoting Meach, this unusually large variation in brightness indicates that the object is highly elongated with a complex, convoluted shape. And so let's delve deeper into its shape. Asteroids, meteors, and comets from our solar system typically appear as large, chunky boulders with proportions where their width is not significantly different from their length. However, Oumuamua presented itself as a large, elongated rocky cigar, estimated to be between 100 and 1,000 meters in length and with a maximum width of 35 meters. To put it into perspective, you could line up to 10 football fields along Oumuamua's length, while its width could barely accommodate 2 bowling lanes. Images from the ESO also provided insights into the object's color and composition. Quoting Meach again, we also found that it had a reddish color, similar to objects in the outer solar system, and confirmed that it is completely inert without the faintest hint of dust around it. This indicated that Oumuamua was a dense, dry object made of rock and metals, although its surface may have been reddened by exposure to cosmic rays over millions of years. Based on these observations, the team in Hawaii proposed that Oumuamua had been freely wandering through the Milky Way for possibly hundreds of millions of years before encountering our solar system. Clearly on a journey of its own, indifferent to our curious gazes, the object continued along its trajectory observed by more telescopes including NASA's Hubble and Spitzer. It crossed Mars's orbit on November 1, 2017, and passed Jupiter's orbit in May 2018. By January 2019, it had moved beyond Saturn before departing our solar system and heading towards the constellation Pegasus. Based on its trajectory, astronomers from Hawaii and NASA speculated that Oumuamua might have originated from the general direction of the star Vega in the constellation Lyra. However, this remains speculative, as it is impossible to confirm. We do not know precisely when Oumuamua embarked on its journey or when it may have passed through Lyra before making its brief visit to our solar system. Its journey among the stars likely began hundreds, if not thousands, of millions of years ago, when the observable constellations were in different positions. To recap, soon after Oumuamua was discovered, astronomers had a rough idea of its appearance and trajectory, but were clueless about its origins or true nature. This uncertainty sparked a lively debate with intriguing hypotheses. Initially, astronomers split into 2 camps, Team Comet versus Team Asteroid. First, let's clarify the basic differences between comets and asteroids. An asteroid is a rocky object smaller than a planet, typically orbiting the Sun. Comets, on the other hand, are composed of ice and dust. When a comet approaches the Sun, it heats up and releases gases and dust through a process called outgassing. This release forms a comb or tail. Oumuamua's observed acceleration aligned with comet-like behavior. Comets accelerate greatly as they near the Sun due to their highly elliptical orbits. However, there were 2 major problems. Oumuamua accelerated even as it moved away from the Sun, and it showed no signs of outgassing, lacking a comb or tail. Despite its cigar-like appearance, Oumuamua didn't leave behind any trail of just smoke or gas. Astrophysicist Roman Rafikov from the University of Cambridge proposed an alternative theory, published in Quantum magazine in October 2018. Rafikov dismissed the comet theory, arguing that an object of Oumuamua's elongated shape, if composed of ice and dust, would have disintegrated due to its speed and acceleration. He also ruled out the asteroid hypothesis due to its highly unusual shape. Rafikov's hypothesis is more dramatic and possibly unsettling. It begins with the demise of a star that has consumed most of its nuclear fuel. As this star dies, it leaves behind a small, incredibly dense core known as a white dwarf, exerting immense gravitational pull. This gravitational force is potent enough to shred asteroids, moons, and even planets, breaking them into large fragments that collide and fracture into smaller pieces. According to Rafikov, Oumuamua is one such fragment, a messenger from a deceased star. As a side note, researchers at the University of Warwick predict that our own solar system may meet a similar fate when the Sun eventually evolves into a white dwarf, potentially tearing apart celestial bodies in a cosmic spectacle. In essence, Rafikov's theory offers a glimpse into cosmic horrors, distant worlds torn asunder by dying stars, adding a profound layer of mystery to Oumuamua's brief visit to our solar system. But imagine if that world were inhabited. What if it managed to send one final message out into the vast emptiness of the cosmos? Alternatively, what if that world was thriving, but decided it would be intriguing to dispatch a vessel towards a distant galaxy, aiming for a distant sun? Here's the implication: Oumuamua could potentially have been an artificial construct, some form of extraterrestrial spacecraft paying an unexpected visit to our star system. Such an idea might seem more suited to ethologists and fringe scientists, often distanced from the skeptical scrutiny of mainstream science. However, accredited astronomers did not dismiss this hypothesis outright. Instead, they sought evidence either to validate or refute it. In January 2018, a team led by Amaya Enriquez from the Department of Astronomy at the University of California, Berkeley, published their paper titled Breakthrough Listen Observations of Oumuamua with the GBT. Quoting from their findings, "It has long been theorized that advanced extraterrestrial civilizations, if they exist, might send probes to other stars for exploration or communication purposes. These interstellar probes would likely utilize communication technologies operating in the radio frequency band." Thus, Enriquez and her team initiated an observation campaign targeting Oumuamua using the Robert C. Byrd Green Bank Telescope. Their objective was to determine whether the cigar-shaped object emitted radio signals consistent with technological origins. The presence of this interstellar messenger presented a rare opportunity to conduct a search for exceedingly faint transmitters, a pursuit unparalleled in any previous SETI endeavors. To provide context, SETI stands for Search for Extraterrestrial Intelligence, a collaborative effort involving institutions like NASA, the Planetary Society, and the SETI Institute. The overarching goal, as defined by the Planetary Society, is to answer the profound question of whether life exists beyond Earth. Over a span of 2 weeks, the Berkeley researchers meticulously observed Oumuamua's complete rotational cycle using the GBT's 4 distinct receivers. Each receiver operated across various transmission bands ranging from 1.1 to 11.6 GHz. Their focus lay particularly on detecting narrowband signals with a resolution of 3 Hz, capable of revealing drifting sinusoids within a drift rate range of plus or minus 2 Hz. Such emissions, if detected, could potentially signify the presence of a transmitter aboard Oumuamua. The study concluded with the statement, "Our initial findings indicate no narrowband radio emissions originating from the direction of Oumuamua during any rotational phase." Did Enriquez and her team thereby debunk the notion that Oumuamua might be an alien probe or an automated spacecraft dispatched by an extraterrestrial civilization? Abraham Loeb, chair of Harvard University's Astronomy Department, presented a contrasting viewpoint. In a Scientific American article dated September 27, 2018, Loeb proposed an alternative hypothesis, the technological relic. According to him, it's conceivable that we may encounter technological artifacts traversing our solar system, lacking detectable functionality, remnants of equipment that lost power over millions of years of interstellar travel, now transformed into cosmic debris. Abraham Loeb highlighted data from the Kepler satellites indicating that about 25% of observable stars might host potentially habitable planets akin to Earth. Some of these planets could have evolved advanced civilizations capable, like ours, of launching various spacecraft and probes into space, which over time could have become relics awaiting analysis by space archaeologists. Loeb speculated further that the first artificial relic might have been identified just recently when the Pan-STARRS sky satellites detected the first interstellar object in our solar system, Oumuamua. He found it intriguing how Oumuamua deviated from its expected orbit, a deviation that might be explained by outgassing, though no coma or tail was observed. Could Oumuamua possess an artificial engine? Even if it turns out to be a natural rock, suggested by its lack of radio emissions, Oumuamua remains remarkably unusual by numerous standards. On November 1, 2018, Abraham Loeb and co-author Shmuel Bialy published a follow-up article elaborating on the relic hypothesis. They proposed in this new piece that Oumuamua might be a light sail or solar sail. Quoting from their paper, considering its potential artificial origin, one plausible scenario is that Oumuamua is a light sail drifting in interstellar space, possibly a remnant of advanced technological equipment. A light sail is a type of spacecraft designed to utilize radiation pressure emitted by stars for propulsion. Radiation pressure is the transfer of momentum from photons when they strike the surface of an object. While in everyday situations this pressure is minimal, in the vicinity of stars where vast quantities of photons are emitted, it becomes significant, akin to a form of star wind. The concept of light sails has been explored and tested by our civilization through projects like the Icarus Project and the Starshot Initiative. These technologies could potentially be used for transporting payloads between planets or even between stars. According to Loeb and Bialy, when Oumuamua entered our solar system, it may have received a propulsion boost from this starlight, potentially explaining its observed acceleration. However, there's a significant caveat. For radiation pressure to cause the observed acceleration of Oumuamua, the object would need to be extremely thin with a very high mass-to-area ratio. globe and Bialy themselves estimated Oumuamua to be about 0.3 mm thick and 20 meters in radius, dimensions that do not align with data collected by the Very Large Telescope and other observatories. Therefore, while the light sail hypothesis is intriguing, it faces challenges in matching the physical characteristics observed for Oumuamua. On March 22, 2023, a study published in the journal Nature by Assistant Professor Jennifer B. Bergner from the University of California, Berkeley, and researcher Daryl Z. Seligman from Cornell University provided a new perspective on Oumuamua's mysterious acceleration. According to their research, Oumuamua likely began its journey as an icy planetesimal. Planetesimals are small bodies composed of rock and ice that form in the protoplanetary disks around young stars. These objects gradually merge to form planets in developing planetary systems. In our own solar system, asteroids are examples of leftover planetesimals. Similarly, Oumuamua was hypothesized to have originated as a large chunk of ice, similar in composition to a comet. In this model, Oumuamua started its existence as an icy planetesimal. During its journey through interstellar space, it was irradiated at low temperatures by cosmic rays. As it passed through our solar system, it experienced warming, which could explain its acceleration without exhibiting typical cometary activity like a tail or coma. This new theory offers a plausible explanation for Oumuamua's behavior based on its assumed composition and journey through space. The model developed by researchers Jennifer B. Bergner and Daryl Z. Seligman sheds new light on Oumuamua's behavior as it traversed the Milky Way. According to their study published in Nature, Oumuamua likely absorbed high-energy cosmic rays from supernovas during its interstellar journey. These cosmic rays may have interacted with the planetesimal's water ice, converting a significant portion of it into hydrogen, which remained trapped within the ice. When Oumuamua entered our solar system and approached the Sun, the heat from the Sun caused the trapped hydrogen to be released. Unlike typical comets that release heavier gases like carbon monoxide or carbon dioxide along with dust, the release of hydrogen acted as a propellant without dragging dust along with it. This hydrogen release, as explained by the researchers, resulted in the acceleration observed in Oumuamua. In their own words, we report that the acceleration of Oumuamua is due to the release of entrapped molecular hydrogen that formed through energetic processing of an H2O-rich ice body. This finding provides a natural explanation for Oumuamua's acceleration without needing to resort to more exotic hypotheses. Professor Bergner emphasized, "We don't need to invoke anything super exotic to explain this behavior." This clarification diminishes the mystery surrounding Oumuamua's speed boost, providing a plausible scientific basis that doesn't require considering it as a technological relic, despite the intriguing possibilities such a hypothesis raises. We've often referred to Oumuamua as our preferred ISO or interstellar object in this discussion, implying it's not alone. Indeed, 2 years after its discovery in August 2019, amateur astronomer Gennady Borisov and his homemade telescope identified the second interstellar traveler, 2I Borisov. Astronomers anticipate that advancements in technology will enable the detection of up to 7 ISOs passing through our solar system annually. However, the challenge with objects like Oumuamua and Borisov is their lack of a fixed orbit around the Sun. They traverse our system before disappearing forever, making extended studies virtually impossible with Earth-based telescopes. While crafts like the Comet Interceptor from the European Space Agency could approach them in the future, there's a call for more specialized missions. In February 2024, Alan Stern, principal investigator for NASA's New Horizons mission, proposed the development of a dedicated robotic spacecraft, an interstellar object explorer. Stern and his colleagues outlined that an IOE flyby mission could be executed for less than $1 billion, a potentially modest sum depending on the space agency's financial outlook. A significant portion of this budget would fund a payload including a panchromatic visible imager, a color imager, an IR mapping spectrometer, and an ultraviolet spectrometer. These instruments would gather crucial data on the geology, color, composition, and rotation of both the interstellar object and its associated tail. Alan Stern's paper outlines the Interstellar Object Explorer mission with a detailed plan spanning 13 years and 3 phases. The first phase, lasting up to 10 years, is termed the loiter phase, during which the spacecraft remains dormant, awaiting the passage of an interstellar object. Once an ISO is detected and deemed interceptable, the IOE will enter its second phase, interception and flyby, expected to last up to 2 years. This encounter may occur around 3.3 astronomical units from Earth, roughly 150 million kilometers away. Following the flyby, the IOE will proceed to its third phase, post-flyby data downlink. Over the course of 1 year, using a 34-meter deep space network antenna, the IOE will transmit the collected data back to Earth. With a budget estimated at $1 billion, the IOE mission prompts the question of whether the scientific insights gained will justify the investment. Alan Stern argues that studying ISO's remnants from the formation of planetary systems around other stars will significantly enhance our understanding of planetesimal formation and evolution in both our own and exoplanetary systems. This mission, he asserts, represents a crucial step towards unraveling the mysteries of our solar system's origins and exploring those of distant worlds. In anticipation of future ISO discoveries, astronomers and space enthusiasts alike eagerly await the next wanderer to emerge from the depths of interstellar space, hopeful that it will provide further keys to the secrets lying beyond our solar system's borders. And that's it. Thanks for joining us on Spaceverse, where we explore the mysteries of space, from interstellar objects like Oumuamua and 2I Borisov to the future of space exploration. Don't forget to subscribe for more updates on cosmic discoveries and the latest in astronomical phenomena. Stay curious and keep exploring the universe with us.